Electrical power systems are integral to the functioning of modern society, but they are also among the most dangerous. This discussion will outline the structure of electrical power systems, methods for assessing their safety, and protocols used to ensure regulatory compliance across industrial environments. Typically, a building's power flows into substations, which distribute electricity to various sections of the facility. Components within these substations include transformers, switches, circuit breakers, GFCIs, relays, and other equipment designed for power management and protection. While each device plays a distinct role, all require thorough evaluation to ensure operational integrity, safety, and long-term reliability. Before delving into testing methods, it is important to consider the consequences of neglect. Consider a circuit breaker. Over time, its internal lubrication may degrade, leading to mechanical binding. Imagine a faulty motor startup causes a power surge through that breaker. The trip unit may correctly signal the breaker to open, but the mechanism fails to respond. The resulting overcurrent blasts through the system, starting a fire, damaging equipment downstream, and halting production, costing thousands in lost time. An on-site electrician, unaware of the full hazard, attempts to remove the stuck closed breaker. This action triggers an arc flash. Even with protective gear, the outcome is devastating. An arc flash or high-voltage electric shock is easily fatal. Such an incident can quickly escalate, jeopardizing additional personnel and first responders. Afterward, OSHA investigates and finds that although infrared testing had been performed, none of the standards outlined by the NFPA were followed or documented. The real issue, mechanical binding from dried lubricant, was not detected. Had qualified personnel been brought in to perform thorough inspections, the entire disaster could have been prevented, while hypothetical. This scenario closely mirrors real-world events that occur with disturbing frequency. Many facilities operate under the run-to-failure philosophies rather than structured maintenance schedules. Though seemingly cost-effective in the short term, this approach significantly compromises both safety and reliability. How, then, can a plant manager determine whether their facility's electrical infrastructure complies with modern safety standards? The first step is understanding the applicable codes and regulations. Guidelines for electrical testing and maintenance are outlined in the NFPA, NERC, IEEE, and OSHA. The NFPA 70B elevated from a recommendation to a mandatory standard enforceable by OSHA in 2023, advocates for a structured preventative maintenance program with testing intervals not exceeding 3 years, as well as defining the tests required. Similarly, the NFPA 70E addresses arc flash and electrical shock hazards by requiring regular testing, proper use of PPE, and detailed hazard analysis. The NERC reliability standards, PRC 005 and PRC 006, are mandatory for power generation and transmission facilities. These focus on integrity of systems critical to the electric grid. IEEE Standard C37.09 provides comprehensive procedures for verifying the operational and safety performance of electrical equipment, including dielectric, mechanical, and thermal evaluations. Finally, OSHA 1910.269 requires that electrical systems be maintained in safe operating condition, with testing and maintenance forming a cornerstone of workplace safety compliance. The common thread across all of these standards is clear. Electrical equipment must be routinely assessed, documented, and maintained. Even with these standards in place, facility managers must stay alert to warning signs that signal a more urgent need for inspection. Red flags include missing acceptance testing at installation, outdated or absent test reports, antiquated or outdated equipment, high trip counts, outdoor exposure, recent fault events, and unexplained performance anomalies, all of which suggest increased risk of degradation or failure. In all cases, urgency increases when test data is missing, outdated, or inconsistent with manufacturer or industry benchmarks. Understanding the standards is essential, but conducting testing is what provides true protection. Much like a medical exam, No single procedure can fully evaluate a component's condition. Instead, a combination of assessments is required to gain a comprehensive understanding. A disciplined testing routine not only verifies that equipment functions within specifications, but also enables predictive maintenance based on long-term data trends. Comparing current results with historical baselines helps identify early signs of degradation and schedule interventions before a failure occurs. A quick way to know if a substation has been tested is to locate tested stickers left by technicians. These stickers should include whether the component passed or failed, the initials of the technician who tested it, company name and phone number, the date tested, job number, and when applicable, whether the component was just tested, repaired, rebuilt, or retrofitted. For each tested sticker, the plant should also have test sheets to match. The sheets should clearly indicate pass or fail, calibration IDs of the test equipment, the date, serial number, temperature and humidity, as found, as tested, and as left values, test currents used, and allowable tolerance ranges following manufacturer specifications. A test sheet that is missing information is cause for alarm that the testing technician was untrained or failed to fully follow standard procedures. The next thing to look at would be the environment the electrical equipment is in. Breaker panels must be cleared by certain footage based on the rated voltage. The NFPA 70E 130.5 and IEEE 1584 also define standards for shock hazard and arc flash analysis for substations. If these studies have been performed, they are identifiable by a label on the substation panels. These studies are now mandatory, but many substations are still out of code today. Some substations are located within the vicinity of working personnel, and it is paramount to ensure that employees understand the hazards involved with working nearby. Also, check the room for fire extinguishers, arc flash gear, and insulated blankets. How about what the room itself is made of? If an arc flash occurred, would the rest of the building be safe? What other environmental hazards might cause electrical components to quickly fail? A common culprit is the weather. In the substation room, look for signs of water leakage. Standing water on the floor, wet marks, and rust are telltale signs. If the air is corrosive, such as from nearby cooling towers, factory chemical use, or even salty air from nearby seawater, that will also cause rapid rust formation. Check cubicle panels for rust, pitting, corrosion, water damage, and missing paint. Check any ground cables to see if they are corroded or disconnected. There are also many environments where dust and debris make their way into substations. This can be anything from typical factory production dust to new construction kicking up dirt. If the outside of the substation is dirty, there is a good chance that the inside is too. Additionally, look for signs of pests. It is common to find circuit breakers that contain dead animals, nests, insects, and waste in them. Pests can get into mechanisms and cause them to bind, cause extra wear from their excrement, chew through wiring, and create unwanted short circuits. How does the substation sound? Is there excessive electrical noise or vibration, buzzing or hissing? That is a telltale sign of loose hardware, corona, or leakage current. Do the lights flicker? Is there records of breakers nuisance tripping? Is there unexplained failures of sensitive electrical components in the facility? These things indicate various electrical problems. You also want to check the substation and floor for debris coming from the substation components. Hardware that has fallen out, and signs of damage like dents, cracks, or paint scrapes. You also want to look for visual signs of arcing or flash damage, such as scorch marks and melted components. Next, you should identify if equipment is obsolete. Common components that fail with age include breakers with dashpots, old mechanical relays, components containing asbestos, Bakelite, polychlorinated biphenyls or PCBs, cloth-insulated wiring, rotary converters, phenolic panels, knife switches, and exposed fuse disconnects. These should be replaced, rebuilt, or retrofitted. If a trip unit has been in service and the settings have never been changed despite updates to machinery and other protected components, The facility may be out of date on its power surveys, and the breaker may not be protecting the equipment the way it is meant to. Each type of equipment in a power system demands a specific set of tests. Let's focus on circuit breakers, beginning with low voltage. To verify they'll perform correctly during fault conditions, we begin with primary injection testing. The brain of a low voltage breaker is the trip unit, an internal control system wired into sensors that monitor electrical current. It's programmable and reacts to different types of faults. The four key trip functions are long time delay, which protects against sustained overloads. It allows minor overcurrents to persist briefly, but trips before the system overheats. Short time delay allows short bursts of high current from things like motor startups, but trips quickly if those currents continue too long. Instantaneous trip provides immediate protection if current spikes to dangerous levels, like during a direct short. Ground fault detects current leakage outside the intended path, a key protection against fire and shock risks. Not all breakers have every function, but it is imperative that all elements are thoroughly tested. A delayed trip, as we have thoroughly emphasized, risks equipment damage, shock hazards, fires, arc flash, downtime, and OSHA fines. Premature tripping can also shut down systems unnecessarily, leading to expensive downtime and untrained personnel tampering with settings. Primary injection gives us the most accurate, real-world simulation of these trip conditions. The test set generates a controlled high current at low voltage, safe for technicians and non-destructive to the breaker. We document trip times and compare them to factory specifications, verifying that the trip unit is operating as intended. Once we've confirmed the breaker trips correctly, we assess how well it conducts electricity through contact resistance testing. Inside every breaker are contact points, often made of copper, silver, or tungsten, that carry the system's current. Over time, the contacts can degrade from corrosion, arcing, or loosened connections, increasing resistance at the junction. Excess resistance causes localized heating, electrical stress, and, in extreme cases, arc flash or fire, but these issues are invisible without testing. Using a ductor, a low-resistance ohm meter, we inject high current through the closed contacts and measure the voltage drop to calculate resistance in microohms. We expect low, consistent values across all phases. Elevated or uneven results indicate worn surfaces, misalignment, bad adjustments, or contamination. This test verifies that contacts are properly seated, coatings are intact, and internal connections are tight. If problems are found, we can perform targeted maintenance like cleaning, retorquing, or rebuilding. The next test checks not where electricity should go, but where it shouldn't. Inside each breaker are insulating materials that prevent voltage from leaking to the frame, to nearby components, or to ground. But insulation degrades over time due to heat, moisture, dirt, and electrical stress. We use an insulation resistance tester, commonly called a Megger, to apply a high-voltage DC signal, often between 500 and 5,000 volts, depending on the equipment rating. The Megger measures how much current leaks through the insulation. High resistance means the insulation is intact. Low resistance means contamination, aging, or internal damage. Degraded insulation is a silent threat. It can cause current to arc out of place, leading to equipment failure, injury, or worse, and it often goes unnoticed until a breakdown has occurred. After all electrical tests are complete, we physically examine the breaker, because even the best readings can't detect mechanical failure. Breakers are complex machines. Springs fatigue, bearings bind, lubrication dries up, and components fall out of adjustment. These issues slow response times or prevent operation entirely. During inspection, we check the racking mechanism, rails, and alignment, contact surfaces for wear, pitting, and proper closing force, internal bushings and linkages, springs for rust or weakness, grease condition, clean, smooth, and effective, or dried and contaminated, signs of heat, moisture, or contamination. Just like an engine needs oil changes, circuit breakers need to be cleaned, lubricated, and adjusted regularly to prevent failure during a critical event. Medium voltage breakers, typically used in larger industrial or utility settings, are similar in purpose but a little different in design. Instead of a built-in trip unit, they rely on external relays to send open and close commands. As a result, primary injection isn't applicable, but other tests remain vital. We perform Ductor and Megger testing the same as in low voltage breakers, but we also perform additional tests due to the added electrical components and higher voltages. High-pot testing is a high-voltage insulation test that simulates extreme stress to ensure the breaker's insulation can withstand fault-level voltages. High-pot testing can be done with AC or DC, depending on field conditions. If the insulation allows any current to leak through, the breaker fails. This test is especially important at higher voltages, where even minor insulation defects can become deadly. In timing tests, we measure how quickly the breaker opens and closes, down to the millisecond. Timing matters. A breaker that hesitates even a few seconds can allow a fault to escalate, causing major damage. We also check that each phase opens and closes in sync. Uneven timing can be related to internal strain or improper contact sequencing. We also test the close and trip coils to ensure they still function at a reduced voltage, like during brownouts or battery backup scenarios. According to ANSI and IEEE, coils should still operate at around 70 to 85% their rated voltage. If they don't, the breaker might not respond in an emergency. We mainly focus on circuit breakers, but other components have similar tests that verify their function in different ways. Transformers are tested for power factor to detect insulation aging, turns ratio to ensure correct voltage transformation, and winding resistance, offering insight into internal integrity and performance efficiency. Switches, though simpler, are checked for continuity, insulation, and mechanical operation. Medium voltage switches also require high-pot testing. GFCIs, designed to protect against ground faults, are tested using ground fault primary injection, in addition to basic insulation and mechanical checks. Power cables undergo very low frequency or VLF testing and insulation resistance checks to ensure durability and fault-free transmission. Busbars and conductors are assessed primarily for continuity, ensuring proper current flow. Each of these evaluations plays a role in a broader, condition-based maintenance strategy. According to the NFPA 70B, it is not enough to simply perform these tests. They must also be recorded, reviewed over time, and used to guide future maintenance decisions. Equipment without a well-documented test history represents a blind spot for both compliance and operational risk. When a breaker fails a test, action is needed. At that point, facility managers typically have three paths to choose from. The first is buying a new breaker. That might sound like the obvious solution, but in reality, it comes with a high cost, both financially and logistically. New breakers are expensive, often with long lead times, and in many facilities, the models they need are no longer manufactured. The second option is to have the breaker repaired. This is a quick and cheap means of keeping substations running, but it only targets the immediate problem and doesn't provide a cover-all solution for other components that are wearing out. The third, and in many cases best option, is to have the breaker professionally rebuilt. Rebuilding restores the breaker to like-new condition at a fraction of the cost of replacement. It also supports recycling and sustainability goals, keeps your system design consistent, and helps extend the useful life of your equipment. Not every breaker can or should be rebuilt, but when it's a viable option, it saves time, money, and waste. And when combined with a solid maintenance and testing program, rebuilds can give a plant decades of reliable protection. A good plan is to have spares tested and, if necessary, rebuilt before planned shutdowns, so reliable backups are available if in-service breakers fail. In the end, we can take any mystery out of electrical safety. When auditing an electrical system, we can see proactive attention to safety in documentation, testing, and planned maintenance schedules. A compliant electrical system should have documented acceptance tests, available test reports dated within the last 3 years, records consistent with manufacturer's specifications, a structured preventative maintenance schedule, records of repairs, rebuilds, and replacements, and spare breakers available that have passed electrical testing within the last 3 years. These conditions allow managers to monitor and predict when maintenance is necessary and transfer outages from unplanned surprises to controlled, safe events. With systems so dangerous, proactiveness is essential.